For this video, I'll be working through question 2 of the Level 2 2015 Waves exam. Question 2. Tom uses a convex lens as a magnifying glass. He puts a petal of a flower 2 centimeters in front of the lens to study it. The lens has a focal length of 5 centimeters. Calculate the distance of the image from the lens. Right, so we have distance to the object as always, and it's a, just double check, it's a convex lens. I'll put a quick picture of the convex lens so I can refer to it in my head. Convex lens, just the distance to the object, it says is 2 centimeters, 0 centimeters, and the lens is a focal length of 5 centimeters. And because it is a convex lens, produces a real image. Anything with a real image has a real focal point, which means the focal point is positive. If it's a concave lens have negative focal length because they produce virtual images, so on and so forth. Right, so we have the formula 1 over f equals 1 over gi plus 1 over go. There we go. In other words, distance to image is equal to 1 over f minus 1 over go. Take the inverse of that because it's the inverse of di, and that gives us negative 3.3 centimeters. And because it's a negative, it's a virtual image. Virtual image, and let's just double check that. It's a focal length of 5, and he puts it in front of the focal length. So yes, it will have, it will be a virtual image. If you're behind the focal length for both convex mirrors, convex lenses, and concave mirrors. If you're between the focal length and the mirror, focal point and the mirror or the lens, it's always a virtual image. Took me a while to spit that out. Right, so next question. Tom goes to the pool, shines a red laser into the pool. He notices that even though the light bends, the light ray bends, it doesn't change color. Explain why the color of the laser remains the same. So the color depends on the wavelength or the frequency. So I'll just put color depends on frequency. Butchered the frequency. And frequency, let's see, remains constant when changing mediums. You quite often see lasers, the color of them is measured in wavelengths, like 532 for green, or 650 for red, or 410 for blue. But frequency is what remains constant. The velocity either speeds up or usually slows down. If it's going from air to anything else, it slows down. That means the wavelength changes. Yes, the wavelength changes, gets shorter, but frequency remains the same, and that's what you see. And frequency also has to stay the same because you've got conservation of energy. Right, onwards and upwards. Next question. Tom shines a red laser at an angle of 40 degrees to the surface of the water of the pool, as shown in the diagram below. Refractive index of air is 1, refractive index of water is 1.33. Now I've given you the angle from the boundary to the incident ray. I've already drawn it in straight away, but when you use Snell's, so you're going to use Snell's law, n1 sine theta 1 is equal to n2 sine theta 2, and the biggest thing you have to try and look out for is that you use the incident angle, which is measured from the ray to the normal, or perpendicular to the surface, or right angles to the surface, or tangent to the surface. They're all synonyms for the same thing. So we need to this angle here that we need to measure. So this is, we're going to call this theta 1, and this is going to be theta 2, or theta r for refraction. So this is either theta 1 or incident angle and refracted angle. Right, let's get on with the calculations. I've written my formula up there. What I'm trying to find is theta 2. I have theta 1, 90 minus 40. Theta 1 is equal to 50 degrees. I'm going to rearrange this here for theta 2. So what I want to do is go N1 sine theta 1, move the N2 onto this side by dividing both sides by N2. N2 equals sine theta 2, and I'm going to take the sine inverse of both sides, sine inverse. Can you see that? Yep, and that is equal to 35 degrees. There we go. And just to double check, when we go from fast to slow, or low refractive index to a high refractive index, it always bends towards the normal. The other way around, you get total internal reflection if you get close to the critical angle. Anyway, 35 degrees, yeah, that seems reasonable. And two significant figures. Our answer had to be two significant figures. Just back up to here as well. Everything else was two significant figures. So we always go for the least amount of significant figures. So I've used 2 here. They gave us 3 for the refractive indexes, but the least significant figures is 2. So my answer needs to be 2. Right, that's that done. Now this is a doozy of a question. Here we go. Can you see that? Go up a little bit further. The coin is at the bottom of the pool. Tom looks at the coin from above and sees an image of the coin as shown in the diagram below. Now this is quite fun. You can do this with an ice cream container. Don't fill it with water. Put a coin or anything that sinks in the middle. Put your eyes so they can't see it just, and then fill it with water, and then all of a sudden it'll appear. So that's the water bending the light, so you can see the coin. Write a comprehensive explanation for why the rays bend and how the image of the coin at the bottom of the pool is formed when Tom looks at it from above. So we'll just start off with rays bent, because they do bend in here. They bend at the boundary before they reach Tom's eye. Reach Tom's eye. That's the bend. Yep. Why do they bend at the medium boundary? Medium. You see that? I'll go up a little bit. Medium boundary. Rays bent away from the normal. Away from the normal, and I can just put a wee normal line up here. I'll just dot that in. That's the normal line up here. It's normally dotted. Put it down here as well if you like. That's just perpendicular. Right angles or tangent all mean the same thing. As air has a lower refractive index than index than water. I.e. light travels faster in air than it does in water. In air than water. And that's what a refractive index is, really. You can think of it as a percentage if you flip it round. So if you get 1.33, you take the inverse of 1.33, it should give about 0.75, which is about 75%. So it travels 75% of the original speed, which is 3 times 10 to the 8. If you go to glass, it's about 1.5. It was about 65% of the original speed. So the higher refractive index, the slower the light goes, and that's pretty much the sum of it. So that's why they bend. They've been away from the normal as the air has to go from a lower refractive index to a a higher refractive index, I should say, to a lower refractive index, and Tom sees the rays. So this is the tricky part, which I think it's a bit. Yeah, anyway, so we see the light rays coming from the coin. The photons hit the coin, bounce off. They get out of the water. So Tom sees the rays being straight, but really they're bent. Which is, I don't know if that's entirely true. But yeah, I suppose it is. So he does. Tom sees the rays as being straight, but are really bent. Really, they are bent, and that's why it appears to be closer. Let me see that. Closer than it is. It really is. You could probably talk about this question quite a lot. There's quite a bit in it, but that's probably enough for this question. So let's just double check we've actually answered it. Write a comprehensive explanation for why the rays bend. We explained that when they go from slow to fast, they bend away from the normal. Why does Tom see it as looking closer? I don't know if that's actually true. Your brain can sort of pick up if it's bending because it looks strange. But anyway, he sees them being straight because normally light doesn't bend commonly. Although I take that back. Let's just forget about that. Right, question done.